Hi everyone, I'm going to go through a simple series and parallel circuit in these two videos. So here is our circuit. You can see that we have an 8-volt battery, 12, 6, and 4 microfarads all in series together. We're going to answer all these questions. The first one is, what is the capacitance of the circuit? Meaning that we want to shrink this down to its equivalent. Now we went through how to solve for the equivalent capacitance for series and parallel. So the series one is the more difficult one, which is 1 over C EQ is equal to 1 over C1 plus 1 over C2 plus 1 over C3. All right, so now we just got to really plug in those numbers and do the algebra. So you can see when I write it out, I'm not writing the microfarads. The units don't cancel. They don't have to be in any standard form. We'll get microfarads out of the final answer. Now, you could easily just start plugging that into your calculator. I'm going to simplify it up a little bit with make it easier to plug in. All right, one of the most common things that people forget at the end is that when we're using the parallel equation, what we're going to get from simplifying our fractions is the inverse of the equivalent capacitance. So you can see here, by finding the common denominator, I got 6 over 12, which is 1/2. So you have to flip both sides. Now what's very important, and I really wish I would put this on the original video, is that when we have capacitors in series, the equivalent capacitance is always going to be smaller than any of the capacitors in the circuit. So you can see that 2 is smaller than the smallest one, 4. That'll always happen. The equivalent of the series capacitors will always be smaller than the smallest capacitor. All right, but right now we found the equivalent capacitance. Shrink that down. So that's part 1. Part 2 says how much charge is drawn from the battery. So how much charge total ends up on that total circuit. So basically what we can do is shrink that circuit down into its equivalent. So we would have our 8-volt battery going to our 2 microfarad equivalent capacitor. And notice that the longer bar for our battery, our power source, is the positive. Okay, so in order to figure out the total charge drawn, we need to use the total voltage and the total capacitance. So there, we're going to use that the total charge is equal to the equivalent capacitance times the voltage of the battery. And just by plugging in those numbers, the 2 microfarads for our equivalent, 8 volts for the battery, we get a total amount of charge of 16 microcoulombs. Okay, now it wants us to find the charge on each capacitor. Now, this is the total charge drawn from the circuit, and remember, the charge isn't going to jump the gap, right? So that amount of charge is going to end up right here on that first capacitor. It's going to be drawn towards there, and what's going to happen is then that's going to pull the negatives from the other side because once the charge is built up on that side of that capacitor, within the space in between, right here, it just polarizes due to just the electrostatic force. So we're going to end up getting negatives on this side equal to what's on the left side, positive, and that's going to polarize and leave positives here. Polarize and pull the negatives within that wire there, and put positives back on here. Make those red. Okay, so again, just because of the electrostatic force, that's what's happening in between the wires from the plates. Again, this charge is not jumping over there, so it's just pulling it and polarizing. So the amount of charge that is on this capacitor is the amount of charge that's on each separate capacitor, right? Because all it does is pull the negatives towards that amount of positives. All right, so if we remember from the first video, the charge on each capacitor is the same. So if we want to write that out as Q1 equals Q2 equals Q3 for each capacitor is going to be the 16 microcoulombs. Now to find the energy supplied by the battery in charging the capacitors, we have to use the voltage of the battery and the equivalent capacitance, because we're talking about the energy supplied by the battery, not any of the energy stored on the capacitor. All right, so we have to use information of the battery. So we have to pick the correct energy equation that has both voltage and the equivalent capacitance. We can also probably use the energy equation that has the total charge drawn from the battery as well. So let's see. Okay, so no matter what equation you pick, you can get the correct amount of energy. You just have to make sure, since you're looking for the battery, that you use the total charge on the circuit and the equivalent capacitance and the voltage of the battery. And no matter which equation you pick, you'll get 64 microjoules. All right, so you can pick whichever one you want. And again, you just use the 8 volts, the 16 microcoulombs, and the 2 microfarads in any of those equations, and you'll get 64 microjoules. All right, now to figure out the energy stored in each capacitor, you need to know the information of the capacitor. All right, so what we don't know about each capacitor is the voltage. So we know how much charge is on each, and we know the capacitance, so that actually makes our lives a little easier, solving for the voltage of each of those. We could do, and just to know how to do that, we know that Q is equal to CV, so by rearranging that, we get the voltage is the charge over the capacitance. So if we take the charge on each capacitor, which is 16 microcoulombs, and divide it by each capacitor value, we would get the voltage across each capacitor. All right, so if we go through that and we do the 16 microcoulombs over the 12 microfarads, we'll get a value for capacitor 1 as 1.33 volts. And then for the next one, you would have 16 microcoulombs divided by the 6 microfarads. The micros all cancel out, but for that second one, you get 2.67. And then for V3, you get 16 over 4, which should be 4 volts. All right. And if we add all of those together, so we have 4 plus the 2.67 plus the 1.33, we'll get a total of 8 volts. So by adding all those together, we get the total of 8 volts, which follows that rule that the addition of the voltage across each of the capacitors in series will equal the total voltage of the battery. So if you want to go through that step, you can. Sometimes you need to. But now we can figure out the energy stored on each separate capacitor using whatever equation that we want to use. So let's try to just go about using a different one for each capacitor. So for the 12 microcoulomb capacitor, we'll use the 1/2 Q times V, and we have to make sure we use the voltage across that 12 microcoulomb capacitor. Okay, so for that first one, for the energy in capacitor 1, which I'm calling the 12 microcoulomb, I got 10.64. Let's do the second one, and we'll use a different equation. We'll use the 1/2 CV squared, and I'll get 21.4 microjoules. And again, I had to use the voltage 2, all right, across that capacitor. And for the third one, let's pick the next equation, Q squared over C. And we just have to make sure we use the 4 microcoulombs. And I got 32 microjoules. All right, one last check here is if we add up the energy stored in each capacitor, we would end up getting 64 microjoules. All right, so that's solving really a simple capacitor circuit with just series capacitors. In the next video, I'm going to do a similar problem, but with parallel capacitors.